Last time we talked about the architecture for GSM. We talked about the three major subsystems, the radio subsystem and the mobility subsystem and the operation subsystem. And we talked about the different components, the interfaces between each of these subsystems and the specifications of these interfaces. We started talking about the handover, and we said that there are like 4 levels of handover that are supported in GSM, including the intra-cell handover and the inter-cell handover, and there is the inter-BSC handover, and there is the inter-MSC handover. So there are 4 levels of handover, depending on whether you perform handover within the same cell, or to different cell, or to different BSS altogether, or to different MSC. So the inter-BSC handover involves the mobile station, because there are some other levels that does not require the engagement of MSC altogether. But this is the law number 3. Yeah. So this one requires the engagement of the MSC. Okay, so that's the depending on this handover, there are the way to decide on this handover is usually by performing certain measurements of the channel at the old base transceiver station and the new one. So usually what happens is that each BTS will perform real-time measurement of the channel to the different mobile stations. Okay, and of course this measurement includes the instantaneous measurement of the channel, depending on the strength of the signal to this mobile station. But of course, similar to what we usually do for TCP and other things, we usually base our decision based on moving average. So we take like the moving average of the instantaneous measurements, and we use that for decision making, whether we do handover or not. So from one BTS to another, if assuming that the mobile station is moving from one BTS to another, typically the channel will decay. The channel to the old PTS will start to decay, and the channel for the new PTS will start to be stronger, right? So this assumes that the mobile station is moving, is driving, it's like the person is driving. Usually GSM supports a speed of up to like 250 kilometer per hour, which is a very high speed. So while the mobile station is moving from one base station to another, the PTS constantly performs these measurements, and each PTS, of course, independently. And when these measurements, like the average measurements, they go to the MSC. So this example assumes that you perform inter-BSC handover. So the MSC will receive the average measurements from one PTS and another, and then it can decide based on certain, they call it handover margin. So this handover margin is used to indicate that the measurement to the old BTS has gone down compared to the new PTS by a certain margin. Why do we need this margin? Why do you think we need this margin? So maybe at this point, okay, once we move any further, we just perform the handover, right? So why do we need to make sure that we have a significant margin before we perform the handover? So this decays and this increases. So maybe at this point we say, oh, okay, so we can start to perform the handover, right? But we have to wait for a certain margin. Why?
no switchover.
Maybe it's not going backward. I will make sure that it is.
It's not going backward. So this is to avoid what they call the ping pong effect, because the measurement of the mobile station might go down, okay, because of fading, not necessarily because the person is moving towards the new PTS. Even if the mobile station is fixed or is not moving, the channel state still, or the channel still goes down or up based on the fading, okay? So maybe the channel at this point will go up and down due to fading, right? Which at this point, if I decide to perform the handover, what will happen is that the channel will go back up again, in which case you perform handover, and then it will go down again because of fading. And we call this a ping pong effect. So you will keep handing over from one PTS to another repeatedly, and that's not good. As we will see, the handover is a long procedure, and it takes time, it takes resources. So to make this decision, you have to be really careful, and you have to be sure that that's the only way you can provide good service to this mobile station. So this is the handover margin.
Doctor, one is having a different frequency, maybe another BTS will be having another frequency. So in the both frequency, it will check that, okay, the signal strength is this one and this signal is, so the handover will take place like this one. And then as soon as handover will take place, then the frequency will also, because this cell one, this may be set to something like this one. No, not like this one.
It's not like this. The channel state is based on what channel the mobile station currently uses. So the PTS, when it connects to a specific mobile station, this mobile station can use one or more frequencies, by the way, because depending on the channel that this mobile station currently uses, so it can switch from one frequency to another even within the same cell. Okay, so this assumes that in the current frequency, the channel goes up and down depending on whether this mobile station is moving or whether this mobile station is currently undergoing some fading or something like this. Okay, so this is for the frequency that the mobile station currently uses. Okay, we don't perform these measurements for all frequencies. For the frequency that the mobile station currently uses, the mobile station can use two frequencies at the same time, one for uplink and one for downlink. And we'll talk about this in more details. So this is the procedure for the handoff. It's a lengthy procedure. It's very complicated. So what happens is that the PTSs, they perform constant measurement to the channel between this PTS and all the mobile stations, okay? And this happens through sending some pilot signals, and then you receive the measurement report. And depending on this measurement report, you measure the received power, and based on that, you can measure the quality of the channel between the BTS and this mobile station, okay? So this measurement will get sent in an average form, okay, frequently to the BSC, to the base station controller. As we said before, base station controller controls multiple PTSs, one or more PTSs, right? So based on that, this BSC figures out that the channel for this mobile station is decaying. So this BSC, in that case, requests a handover. And this request goes to the MSC. So the MSC will receive a request for handover. It's the handover decision. So the BSC will send a handover required signal to the MSC. The MSC might accept or reject that, depending on the situation for the new BSC. So maybe the handoff margin is not met yet, in which case it may actually, before moving any further, it may respond with a handoff reject, and that's it. Okay? So assuming that the MSC finds that there is a handover margin and I can perform the handover to the new BSC, okay, then it sends a handover request to the new BSC. Okay? So remember, you have to make before break. So this is to make before break, which means that it's very important that you do not release from the old base station, from the old PTS, until you make sure that you establish the service with the new BSC. Why? Because you have to make sure that you have no interruption to the voice call, right? So if you decide to say, oh, okay, I will release, I will break the connection with the old BSC, and then I will start to do the connection with the new BSC. This will lead to what? Interruption in the service. So that's not good. So here the handover uses the principle of you have to make before break. So you have to first establish the connection with the new BSC, which means that at some point here, the mobile station has resources allocated here and here. Okay? And that's needed because otherwise we'll have a service interruption. So when the handoff request goes to the BSC will perform resource allocation. As we said before, this is one of the functions of the BSC, is to perform resource allocation. Resource allocation is based on what? Is based on saying, okay, so this PTS has this frequency resources, and I have some time slots available or not. If I have some time slots, at least one time slot in one super frame available that I can allocate to this mobile station, then I can activate that, and I can send a positive acknowledgement to indicate that I indeed have some resources for this mobile station. Okay, so this procedure, even though it's complicated as you can see, but it shows only the happy path. So there are many exceptions here that might happen. So at this stage, or at this stage, or at this stage, that's missing here. Okay? So I did the resource allocation. I sent the channel activation request to the PTS to ask this PTS to allocate this time slot or this physical channel to this mobile station. And I get a positive acknowledgement, which means that now we have these resources reserved. Okay? So I send the handover request acknowledgement to the MSC. So now the MSC is quite sure that these resources are now allocated for this mobile station at the new base station subsystem, or BSS. Okay? So then and only then, it sends a command to the mobile station first to establish the handover access. So the handover access, or the handover command here, establishes the connection end-to-end between the mobile station and the new PTS. So now I have an end-to-end link between the mobile station and the new PTS. So at this stage, the mobile station, until this stage, the mobile station did not release the resources yet. So I have to make sure that this end-to-end link is established between the mobile station and the new PTS. Then the PTS will send a handover complete to the mobile station center, and at this stage only, I can release the resources from the old one. Which means that you have to do everything and establish the link end-to-end and make sure that this link is established and get positive acknowledgement before you start breaking or releasing the resources from the old one. So the MSC here will send a clear command to clear the resources from the from the old BSC and from the old PTS, which means that now these physical time slots are free for allocation in the future. Okay, so this is the logic for handover. As you can see, it's a very lengthy procedure, and that's why you have to be sure that you don't perform this unless you have to. Unless you cannot provide a good service to this mobile station from the old BSC, then you can switch to another BSC. Of course, this scenario is specific for a enter BSC handover, which, as we said before, that's this example.
New BSC is coming. Suppose it is within the same MSC. Okay, so this is for the same MSC or
Yeah, for
when
the same.
it is MSC to MSC, then another it will be.
Yeah, of course, it will be even longer than this. Because you will have another MSC here.
They were correct.
Okay, and there will be some other signals between one MSC and another. Okay.
One question here.
Mm-hmm.
Here, as soon as MSC receive H handover request acknowledgement,
Right.
it will release the handover
No.
command.
No, not right away. No. Until here, you have allocated the resources, but you did not establish. Remember, this is circuit switched. You have to establish the connection end to end. So you need to send a handover command to the mobile station to make sure that you establish the connection end to end. Okay? So you have to establish the circuit, the new circuit, and then and only then you can dismantle the old one. Okay?
So when handover command will go up to the mobile station, then afterwards the connection link is established.
Right.
And as soon as connection is established, then afterward handover complete and then.
Right. Yes. Then after you establish everything, make sure that the handover is complete to the new one. Then you can release the old one. Okay. Until this point,
Both.
the old one is still working. Remember. There's no interruption to the voice call. So until this point, the old one is still working, and then you can switch to this link and dismantle the old one.
The MSC reject the handover.
Right.
Send acknowledgement to the controller that it
Negative acknowledgement, yes, to the old BSC, yes. So in that case, it doesn't want to perform the handover at this point. Okay.
Doctor, how much time this one? How much? 3 milliseconds, 10 milliseconds? This whole complete cycle?
It's in the order of tens of milliseconds, or maybe 100 milliseconds. So it takes some time. And during this time, you have resources allocated on both sides.
But voice, 100 milliseconds, if it is there, then voice, maybe we will not be able to recognize it. But in case of data, this will be a problem in that case.
No, but it will not switch until.
Yeah, exactly. Remember, there's no interruption here. There's no interruption. I will not.
Handover already this process is going.
Yes.
In this case, new.
Okay. So another very important service in GSM is what we call a security. So security are implemented in GSM in 3 different ways. You have access control, which is part of authentication. And as we all know, authentication is to make sure that the person who is accessing the system is really the person that he says he is. Okay, so you want to verify the identity of the person, and of course, logically, this is through the SIM card. So the SIM card is your way for you to authenticate yourself to the system. Confidentiality ensures the concealment of or the secrecy of the communication between the mobile station and the network. So the PTS. So any traffic that goes from the PTS to the mobile station, you should make sure that nobody can tap into it or eavesdrop this traffic and listen to it. Anonymity makes sure, or anonymity belongs to privacy. Privacy, or you need to make sure that the user identity is hidden on the air interface. Okay, so for example, you know that this user has a certain mobile station identifier, which is part of the SIM. Okay, so this MSI is stored in the SIM card. Okay, so you need to make sure that this identifier is not exposed on the air interface, that anyone can take this identifier, because this identifier points to the user, points to the subscription of the user. So you need to make sure that the identity of the user is hidden throughout the traffic. And the way to do that is through what they call a temporary mobile station identifier. So the actual mobile station identifier gets stored in the HLR. And then when you authenticate yourself to the system, the VLR, or the visitor location register, will assign to you a temporary mobile station identifier, which is different from the actual user identifier. And this mobile station identifier will then identify the service of the user, not the user, but identify the service of the user at this location area during a certain period of time. And then it might actually change dynamically. But it has no association with the actual user. Okay? So this way you can hide the identification of the user during the transmission. So this TMSI, it gets assigned at each new location area, so it's dynamic. So this way you can, and it's actually encrypted, of course, as part of the data transfer. So this way you can make sure that not only the information is concealed, but also the user identity is totally hidden during the communication. So to do that, GSM defines 3 different algorithms. Okay, you have the A3, A5, and A8. So A3 is used for authentication, and A5 is used for confidentiality, and A8 is used for encrypting the key, the individual key, and generating what we call a cipher key, as we will see. One thing to notice here is that both A3 and A8 are not, the specification for these algorithms were not originally included in the standard, which means that they are secret, which also means that it's up to the service provider to define these algorithms based on some proprietary specifications that the service provider might have, okay? But A5 is publicly available. So A5 is known. But A3 and A8 might change from one service provider to another, which means that they are not publicly available and they are not part of the standard. Okay, كده? طيب.
Doctor, one more thing. This SIM is like in our ATM we have a chip and...
Yes, this is the SIM card, yes.
Similar to the SIM?
Yes, the
when
SIM.
we insert the ATM, then it will...
ATM? Yeah. So this is the SIM card that you put in the mobile. Yes, this is the SIM card. This SIM card actually has a chip, and this chip has the mobile station identifier. It has a PIN number, so that you authenticate yourself to the SIM. So it has a PIN number. It has the mobile station identifier, and it has A3. It has this algorithm built into it. Okay, as we will see that.
It cannot be duplicated.
Yes? Yeah, it cannot, yeah. So this is the procedure for authentication. So for authentication, remember that you have the access control or the authentication center, which is part of the operation center. Okay, so we talked about that as part of the architecture. And you have MSC, and you have, this is the SIM card, which is, of course, integrated into the mobile station. So the procedure for authentication is based on a challenge response procedure, which means that I will give you a puzzle, I will give you a test. If you answer it correctly, then you are authenticated. So this is based on generating like a random number of 128 bits. And this random number will get sent across the system across the air interface. So this one will get sent. This one is exposed. But you have here an individual key, which is part of the SIM, and you have, of course, this key, which is also a managed or maintained inside the authentication center. So when I send you a random number, both of us will apply A3 at the same time, and we generate what we call assigned response. So this is the challenge that I give you. I give you a random number, and I tell you, generate some response based on this random number. Okay? And I will perform the same operation locally at the authentication center. And we'll both send our signed responses to the MSC. If the MSC verifies the two signed responses and it finds it matching, then this user is authenticated in the system. Okay? So that's how we perform the authentication. So what about confidentiality? Any question for this? So this is straightforward. In fact, by the way, later on, even A3 and A8 have been included in or have been like published on the internet, and that's why it left these algorithms like sort of exposed and leaked. So the security for GSM is not robust anymore. And of course, for 3G and 4G, this has become much more complicated than that. For confidentiality, remember, for confidentiality, the requirement here is to generate a key, and this key will be used to encrypt the traffic along the air interface, which is between the PTS and the mobile station. Okay? So the way we do that is, again, by sending a random number from the authentication center or from the access control component, and then this random number will get sent, and then both of us will apply, not by A3 here, will apply A8. Okay? Both of them are secret. And the outcome here is not by assigned response. The outcome here is a cipher key, which can be used by the PTS and the mobile station. So this, of course, will get communicated to the PTS, and this will be part of the mobile station. Of course, the SIM card is integrated in the mobile station. So the mobile station will have a cipher key, which is similar to the cipher key in the PTS. And both of them will use, which is a symmetric key, of course. This is not like public-private type of key. This is a symmetric key. It's the same key on both sides. Okay? But to generate this key, you apply A8, you apply algorithm number 8 to the individual key that's maintained on the access control system and the SIM card.
So this if cipher key is known, then the encryption can be...
In order for you to know the cipher key, you have to know A8, which is, okay, it's supposed to be secret, but assume that even if you know it, you have to have A8, you have to have the KI, which is an individual key inside the SIM, so you're not supposed to know that, okay? And you have to have access to the random number as well. So the random number gets sent over the air interface, but it's sent once. It's sent once. So if you listen to it, if you listen to this random number, you need KI, okay? And then you need the specification for A8 in order to perform the same cipher key, okay? That's not to say that this is perfect or perfectly protected, but it's a little bit hard.
The KI is the same for both?
Yeah, the KI is stored in the SIM card on one side. Remember, the KI is stored in the SIM card, which is provided to you by the service provider. So the service provider will have a copy of this in the access control system.
The cipher key should be 128 also, same as.
No, not necessarily. Why? The A8 A8 will take 128 and 128 and will apply certain logic to produce 64. In fact, it performs some operations on the 128 bits to produce 64 bits. Why does it have to be 128?
Because
انت نفسك شرحت لما جيتي شرحت قلت ايه؟ I can take 128 and I can take the first 64 and second 64 and do XOR between them. أنا حر. ماشي طيب okay. So this means that you don't necessarily have to have 128 output. صح؟ So I can.
And we should get 128
إيه؟
ciphertext.
لا إيه؟ لا we should apply the ciphertext. You should. The cipher key is 64 bits.
But the text, ciphertext, we should get.
ciphertext اهو ما حدش قال ان هو ولا 128 اهو ده الداتا اهو صح؟ So you need to use this key to encrypt the data. ما حدش قال اللينث بتاع الداتا ايه دلوقتي. لان ده يعتمد على A5. اوكي؟ طيب any questions so far? So this is the authentication and the confidentiality or the encryption across the air interface. طيب. Okay, so basically this is the sort of the end of GSM specification. So this is technically the end of GSM specification. So we talked about the architecture, and we talked about the different services, including handover and security services, right? As we know, GSM is part of G2, second generation. So for GSM, we know that the data services are very, very limited, providing a data rate of like 9.6 kilobits per second, which is suitable for like fax services. You remember we talked about the supplementary services. We said that we have a group fax services, we have SMS and so on and so forth. But definitely it's not enough for like multimedia traffic, for even hatta emails with attachment and so on. So these types of data rates are very small, and they are not enough to provide all data services that we have nowadays. So starting from G2, we all had the ambition to increase these data services. But the question is how? Okay, so we want to increase these data services because we want the cellular system to develop and provide more types of data service applications like web browsing, like multimedia, voice over IP, hopefully like video streaming, something like that. But of course, all these services cannot be provided by this very low data rates. So to do that, the standard developers, they started to look into some ways to increase these data rates. And one fundamental concept that they thought about is to try to increase the data rates with limited changes in the architecture. Okay? Which means that we know that, for example, we have super frame and we have time slots. Okay? So the resources are divided as super frame and time slots, and we have different channels. So we have different frequency channels and different time slots per channel. So we can allocate TDMA and FDMA and so on. So each of these time slots, we can imagine that each of these time slots, they belong to a physical channel, okay, which provides a service to a specific user. So depending on one time slot in a specific frequency range, this user can get 9.6 kilobits per second. Based on assigning the single resource to the mobile station, the physical channel gets established, which requires about all the signaling and stuff to establish the connection, as we have touched on that as part of the handover. So the idea is that the main idea of the first extension to GSM is to say, what about if we bundle these physical channels, okay, into groups? So this way, instead of providing 9.6 kilobits per second, if we can somehow group multiple physical channels into one logical channel, we can increase the data rates. Okay? Which essentially means that we can assign to this user 4 time slots. Okay? But remember, each time slot is allocated to a physical channel, which means that what we essentially do is that we group these 4 channels into one bundle of channels. So they introduced the concept of channel bundle and so on, and so they introduced new concept of bundling the physical channels into logical channels. The good thing about that is that the additions to the system are minimal. So I don't have to change the architecture drastically. And the good thing about this standard, which is part of 2.5G. So this is 2.5G. It's called the high-speed circuit switch data. So the only added thing in HS CSD is this concept of bundling. Yeah. Okay, by bundling multiple physical channels, I can provide higher data rates. Okay, so the advantage of this high-speed circuit switch data is that I don't have to add so many things to the architecture. I don't have to introduce any new component in the architecture. Okay, all I need to do is just to provide some mapping between group of channels into one logical channel and be able to bundle these channels. So the good thing here is that I don't need to introduce anything to the architecture, which means that all the updates are software updates. So if you tell the service provider that all what you need to do is just to update patches on your servers, so this is attractive. So I don't need to dismantle everything and redeploy new hardware and so on and so forth, right? It's still circuit switch data. So these channels are established end-to-end. So you have to establish these circuits, okay? And all we did is just we grouped multiple of these circuits into one virtual circuit, one big virtual circuit. So, so this way you can achieve rates of, this is called the air interface user rate. So this air interface user rate, if you use one physical channel corresponds to maybe 1 time slot or 2 time slots maximum. So this will give you a rate of 4.8 kilobits per second. But if you use 2 of these physical channels as one logical channel, then you can have up to 9.6. If you group 3 of them, then you can have 14.4. And from here to here, the physical channels are bundled together. So if you actually bundle 2 of these channels together as one logical channel, then it's like you are aggregating the traffic. So you can have individual physical channels, and you can use multiple individual physical channels, or you can use a bundle of physical channels together to provide the same aggregated rate. So, so you have now the F4.8, and you have 9.6, and you have 14.4. So these are different bundles of these physical channels. And 2 of these channels correspond to 1 of this channel. 4 of this corresponds to maybe 1 or 2 of this, and so on. Okay? So by bundling all these channels together, you can increase the data rates. As you can see here, the maximum bit rate that you can achieve is 57.6. So I can achieve, so instead of 9.6, I can achieve 57.6 kilobits per second, which is, yeah, it's not drastic, but it's a good expansion. In fact, this can be achieved by using 4 time slots in a super frame by one mobile station. So this corresponds to assigning 4 time slots to one mobile station in one super frame. Type. Theoretically, I can allocate all the 8, in which case I can double this rate. So theoretically, I can allocate all the 8 time slots to one user, in which case I can double this rate. The only limitation with that is that, remember, if you have one super frame which is composed of 8 time slots, right? And this is for uplink. And you have another super frame which also corresponds to 8 time slots in the downlink, right? So mobile stations could be full duplex or half duplex, okay? Depending on what? Depending on the hardware capability, whether the transceiver itself is designed to provide full duplex or half duplex, okay? So if I assign all the 8 slots, this means that I will take the entire super frame for uplink and downlink, which means that the mobile station has to be a full duplex. But if I assign only 4 slots, okay, then I can, from the uplink, I can take these 4 slots, and then on the downlink, I can take these 4 slots, in which case the mobile station doesn't have to be a full duplex, right? So you are using different time slots in the uplink and downlink, right? So this way you can switch from the uplink to downlink. You can switch to different time slots, which means that you don't necessarily have to send and receive at the same time. If I use all the 8, then I'm using all the 8 for uplink and downlink, which is possible, but it requires the fact that the mobile station has to have a full duplex capability. Not all the mobile stations will have full duplex capability. So typically in GSM, most of the mobile stations, they are half duplex. They are not full duplex. So they cannot send and receive at the same time on 2 different frequencies. They cannot do that. A base station can do that, but of course, the base station can do that, but mobile stations cannot do that. So typically, what happens is that the maximum they could do is to use 4 time slots in the uplink, and then they can switch to use the other 4 time slots in the downlink. So this way, they can switch from uplink to downlink in 2 different time transmissions, so they can do that. So the mobile stations are half duplex. So that's why typically in this type of standards, the high-speed circuit switch data, typically we don't go beyond 4. Okay? We don't go beyond 4. So we use 4 time slots in the uplink and 4 time slots in the downlink. And that's why typically the data rates are up to like 57.6 kilobits per second. And this 57.6 kilobits per second depends on certain coding schemes. So using other coding schemes, it can get slightly higher. But this is the typical values for data rates in high-speed circuit switch data. Type. Any questions so far? So based on that, we can achieve higher data rates. It's not fundamentally higher, but at least it's like how many? Like it's at least 4 or 5 times So it's good. And the good thing is that I didn't have to introduce any hardware, I didn't have to introduce anything in the architecture. So what is the disadvantage? The disadvantage here is that the channels that get assigned, the physical channels that get assigned to the mobile station, remember this is circuit switched. Okay? So once you assign these time slots, they get assigned for the entire duration of the session. Okay? Which means that on one hand, this mobile station may not have traffic to fill all these resources all the time. For example, the user is using some web browsing and he switched to another service. So depending on the application that the mobile is used on the mobile station, it may or may not use all these resources, all these time slots. I allocated 4 time slots, but the mobile station did not use all of them for the entire communication, which means that some of these time slots are wasted. Not only that, these physical channels, because they are allocated to this mobile station for the entire session, they get blocked for other voice calls because it's the same channel. It can be used for voice or it can be used for data services. So if one user is assigned 4 time slots, which means that this user will have 57.6 kilobits per second, but other users will starve. They cannot use the other channels for voice transmission or for voice calls. Another disadvantage, which is not written here.
So cost becomes 4 times signals.
Yes, this is true. They actually remember that the bundling of the channel is only logical, but the physical channels are still there. And these physical channels, the amount of signaling that you have to do to establish these channels is proportional to the number of physical channels that you have. So for example, for handover. So for handover, all the procedure that we did will have to be done for every single physical channel. Because again, this bundling is logical. So the amount of signaling that you send back and forth within the system is still proportional somehow to the number of channels that you bundle. Okay, so that's cumbersome. So the amount of signaling for one mobile station, well, for the base station it's okay because the base station has to deal with all these physical channels anyway. But we're talking about the mobile station. It's an overhead on the mobile station because the mobile station now has to send so many signals to establish multiple physical signals, and that's a big overhead. Okay.
It is not like this. These 4 going from one MSC to another MSC. Then he will allocate another 4 free channels and then accordingly it will switch over.
Say that again, sorry?
So this MSC knows that this BTS is having 4 pair of channels.
Right.
Now it is going to another BTS. So in this BTS he will allocate 4 channels, free channels in the same frame. Or you look for a frequency in which super frame in which the 4 channels are free. And then accordingly allocate.
Who will look for that? The MS?
Not MS.
Ah.
BTS or BSC.
The BSC is the one that allocates the resources. Remember, the BSC is the one that allocates the resources. It's the one that performs the resource management or the resource allocation. Okay, so all the mobile station does is to request a service with a specific data rate requirements or a specific application requirements, and then the BSC will try to perform resource allocation to try to decide, okay, based on these service requirements, I need to bundle مثلا 4 different physical channels or 2 or 3 or whatever. Okay, but once we establish the circuit with specific number or a specific group of channels, these channels, they get blocked from all the other mobile stations خلاص, during the entire communication. Okay, even if this mobile station cannot use them. Okay, not only that, the mobile station has to keep sending signaling for all these physical channels which is an overhead on the mobile station. It has to maintain all these channels together. طيب. The other, okay. So we'll stop here and we'll go for prayer, and then when we come back, we'll do this. Okay. So the other extension to the standard to provide higher data services is GPRS, or the General Packet Radio Service. And from the name, as we can imagine, GPRS provides packet switched network, unlike the circuit switched. So for packet switched, as we know, we don't have to establish a physical circuit, which means that we don't have to have the time slots allocated for the entire duration. We can allocate the time slots adaptively and instantaneously, which means that from one superframe to another, we can change the allocation of these time slots to the different users. And this gives us a flexibility and makes sure that we don't waste the resources and assign it to a user that does not have traffic to fill all these time slots. But this has a serious implication, really. So changing from circuit switch to packet switch changes drastically the architecture. So we will not have physical channels. We will not have channels established as physical circuits for the entire duration, which means that all the signaling that we do will have to be different, and the architecture is fundamentally different, which means that we have to add hardware, new hardware, that will provide this packet-based service or packet-switched service. Okay? So using packet switched, as we said, using the free time slots only if data packets ready to send. So we can now assign the time slots to the user based on their demand, based on exactly their demand. We don't give them more resources which they will waste. So the advantage of this is that, of course, this is gives me more flexibility to assign resources and make sure that the resources are utilized efficiently. And GPRS is the first step towards 3G, which is the first standards that are totally packet switched or IP based. So GPRS is also IP based. Okay, but in order for us to provide this packet switched data, we have to add another hardware. So we have to add other components in the architecture to provide this packet switched service, which is parallel to all the MSC and all the other components which are purely circuit switched. Okay. So the disadvantage of this is that more investment needed in terms of hardware. So I have to add new hardware components. There's no escape. There's no work around this. I have to add another hardware to provide packet switched networks. And this hardware includes two totally new components, which correspond roughly to the MSC and to the gateway MSC. So we have a GPRS support node, which is sort of corresponds to the MSC, but to provide the packet switch services. Okay, and we have the gateway GSN, or the gateway GPRS support node, or this is again the door to the other types of networks. Remember, the gateway MSC is the output door to the other types of packet data networks, or other types of networks in general. So we talked about GMSC and the interworking component, which are used to interface with other types of networks. So similarly here, we have the GPRS support node and the gateway support node. And the gateway support node is used to interface with the other types of packet data networks. So those two components are IP-based. And in fact, for GPRS, the mobile stations will get assigned an IP address. In addition to all the other identifiers and so on, the mobile stations will have an IP address. And in fact, this IP address is a private IP address. Private IP address. Okay? Which, of course, a private IP address, we know the difference between private IP address and public IP address, which means that one of the functions of the gateway GSN is to provide network address translation. You know that? Who doesn't know that? You know the network address translation? So network address translation is used to map between private IP address and public IP address. Okay? So when I communicate with the external networks, I have to map the private IP, which has significance only within this network, to a public IP that can be used to communicate over the internet. So this will allow the mobile station to communicate with another node on the internet or another server. Of course, the limitation of this is what is the limitation of private IP?
Number of IP? Number of IP?
No. You have a lot. Remember, one characteristic of the private IP is that it can be reused. It doesn't have to be unique. So there is no shortage of private IPs. But what is the limitation?
These are common addresses. Like 192, 168.
Yeah, because of the fact that they can be reused. So there is no one fixed IP that's unique over the internet, which is unique to this mobile station. You cannot have this. In which case, you cannot have a mobile station that acts as a server. Because a server needs to have a fixed address, right? So you cannot have that. Private IP address is reused. Okay? And that's why it's not easy to have a server on a mobile station and access it from another mobile station over the cellular network. Until today, actually, this is a challenge. Okay? Because of the fact that mobile stations, they use private IPs. Okay, so the serving, this is called serving GPRS support node. Okay? The serving support node it corresponds to the MSC. So you have one mobile station which is supported by one SGSN. Okay? And this one has the functionality of both the MSC and the operation subsystem. So all the authentication for the mobile stations within GPRS, all the billing, all the mobility issues, everything is handled by this serving GPRS support node. Okay? And of course, because now the mobile station has another addressing which is different from all the identifiers that we talked about, MSI and TMSI and all of this, now the mobile station needs to have an address, IP address. So we need another register which is called GPRS register. So the GPRS register will store the addresses of the mobile stations. Okay, which is used for packet level services or packet switched communication. ماشي؟ طيب. Of course, these nodes, they are added to the architecture. So if we add this to the architecture, we can imagine the architecture got really complex. يعني. So you have duplication of hardware. So you have all the MSC and all the AUC and.
All these components are hardware?
Yes. Yeah, these components are hardware, which is added to the architecture. And there is, of course, because they are added components, you have added interfaces. So remember we talked about the UM interface, the ABIS interface, the A interface, and the O interface as part of the GSM architecture. These new components, they add other types of interfaces. They add the GI interface, they add the GN interface. We'll talk about that. before we talk about the changes in the architecture, one of the very important objectives of GPRS, because remember, circuit switched has this quality of service built in. Circuit switched provide constant quality. صح? Because you have a circuit which is totally allocated to you. So the service quality that you get is deterministic because you have fixed resources allocated. صح? But GPRS now provides dynamic allocation. In every super frame you may get 1 slot, 2 slots, 4 slots, 8 slots. You can have all the 8 slots allocated to the uplink and 0 slots allocated to the downlink. Okay? So it's dynamic. So based on that, the behavior that you get is dynamic. So how can we make sure that we have a specific quality of service? A specific quality of service represented by, for example, I need to guarantee a certain data rate, a certain minimum data rate for this mobile station, or a certain delay, or a certain level of reliability. Okay? So quality of service is one of the very important objectives of GPRS. So a quality of service can be defined by different matrix. You can divide the quality of service as a reliability. So GPRS provides course level of quality of service classes. And the mobile station can be assigned to one of these classes. Okay? So you can have class 1 or class 2 or class 3. So it provides only 3 classes. So if you need like very high level of reliability, so you get assigned to class 1, which essentially means that the packet loss, this is the service data unit, the loss rate for the service data unit is in the order of 10 to the power minus 9, which is very, very low. For duplicate service data unit probability, it's again 10 to the power minus 9. So reliability is defined by multiple things. By the amount of service data units that gets lost, or service data units that gets duplicated, or service data units that gets corrupted, or something like this. So all of these are part of the reliability. And by assigning the mobile station to one of these classes, you can get this. So how can the GSN or the GGSN, they can provide this level of classes? They have to adaptively allocate the time slots to make sure that on average you get this. Okay? Which means that if it finds that, of course, this can be like average over time. So if it finds that you have a loss rate which is more than 10 to the power minus 9, it gives you more slots, so you can reduce the number of packet loss. Okay? So on average, it has to guarantee this, and it does that by adaptively allocating the time slots to the different mobile stations.
Class 1 is the highest.
Yes, it's the highest. Yes, class 1, this is the highest, which means that it has the lowest probability of error.
But how they calculate the numbers?
It's based on measurements. So you, if you have مثلا during a certain duration of time, let's say like 1 second, if you have 10 to the power 9 number of packets within a certain duration and one of them is lost, this means that you have a probability of 1 over 10 to the power 9, which is 10 to the power minus 9. Okay? So every 10 to the power 9 packets, you lose 1 packet. So this is very high level of reliability. Okay? So class 2 is less reliable. Class 3 is even less reliable. Same thing for delay. Delay is measured end-to-end. Is end-to-end, I mean between the mobile station and the PTS, only on this air interface. طيب, the delay has also the standard defines 4 classes for delay. You don't have to memorize all these classes. واضح. But يعني the idea is that a quality of service is provided by GPRS through coarse level of classes. Coarse level of, they are not fine-grained يعني. So again, class 1 is the most stringent when it comes to delay. So you have less than 0.5 seconds. 0.5 seconds is a lot. But this is through air interface, remember. This is through air interface. Of course, we're used to like milliseconds and stuff, but this is in wired networks. But in wireless, yeah, it's sometimes it gets that high. And this delay can be like average delay, which means that you can get up and down. So you can get, so you can get a delay over time. So this is the delay over time. So this delay can be like something like this. But the average is less than 0.5. So this is the average. Okay? The 90% percentile, this means that 90% of the time you are less than 1.5. Which means that يعني if you have here 1.5, okay, the delay is definitely less than that, and only 5% they can go up. واضح? Okay? So this means the 95% percentile. Okay? So this is more stringent, يعني, this more, because the average sometimes is loose. So you go much higher, much lower, but the average is 0.5. But when you look at the instantaneous delay, it's very high or very low. So the 95 percentile is more stringent. Okay? So again, these are coarse traffic classes. Unspecified here, this means best effort. So again, class 4 is the lowest in terms of quality of service. And in fact, there is no specification for the delay. I don't have any guarantee for the delay in that class, which means it's best effort. ماشي? It's similar to IP. IP best effort. So I don't have any guarantee. So it can go very high, it can go very low. I don't have any constraint.
But the lowest quality is class 4.
Eh?
Lowest quality
Is?
class 1.
This is the highest quality of service. Highest quality of service means that you have the lowest delay. This is the lowest delay. صح? So you can define the quality of service based on reliability. You can have a delay. So a mobile station can be assigned to class 1 for reliability, class 2 for delay, and so on. You can now. There is also the device classes. يعني a mobile station can belong to one of these classes. This is based on the hardware limitation of this mobile station, which means that the transceiver design in terms of hardware, يعني in terms of circuit design, it belongs to either class 1 or class 2 all the way to class 12. So the higher the class, the more complex the hardware is, which means that to some extent, the mobile station can provide sort of full duplex, half duplex. It can actually work with higher number of channels for uplink and downlink. Okay? Higher number of channels or higher time slots, يعني. Higher number of time slots. So some device classes cannot use more than one time slot. In which case, this reflects on the amount of data rates that this mobile station can get. Okay? So the device class is also one of the specification of this mobile station, based on which it might have, the mobile station might have some limitation, some internal limitation on the actual data rates that it can get. Not only that, remember that based on the traffic class, so here class 1 can use one time slot downlink and one time slot uplink, okay, which means 2 maximum. But here you have an interesting combination here. you have 4 downlink and 2 uplink, but up to 5 maximum, which means that you cannot use 6. Okay? So it's either 5 and 1, 4 and 1, or 3 and 2. So this is the maximum time slots up and down. Okay? Even for traffic, even for device class 12, it can use 4 slots, up to 4 slots, up and up to 4 slots down. But the maximum is again 5. So it can be 4, 1, 3, 2, 2, 3, 1, 4, something like that. So this is, the total is 5. Okay?
So with this total 5, we are getting 50 kbps. While in another case...
Exactly. So depending on this number of slots, you can...
So of course, they can have 4.
No. They cannot have 8 time slots. Yeah. And we talked about this before. We said that if you use all the 8 time slots up and down, this means that you have to have full duplex support. The mobile station needs to have full duplex because you need to support the transmission, receiving and transmission on 2 different frequencies at the same time. So based on these time slots allocated and based on the maximum time slots, table is based on this. The total is based on the maximum time slots. You can estimate the data rates that you get. So if you get 1 time slot, this is the data rate that you get. But remember, this is based on a specific coding scheme. So one of the allocated resources that the base station can perform is the coding scheme. Coding scheme معناها ايه? Remember we talked about forward error correction, or if you add to the data bits, if you add some redundant bits, you can correct the errors when they happen. Not only you can detect the error, you can correct it. Okay? Who's not familiar with the error correction? You're not familiar with error correction, right? So the coding scheme, they are simply, so if you have some data bits, the service data unit, they have some data bits. So you add to some data bits, some they call it CRC codes, or some redundant bits, which perform some combinations of the bits in the data, so that if any of these bits, they get toggled or they get an error, you should be able to, through this combination, correct this bit without having to retransmit. Because we talked about error detection for TCP and these protocols. They use a error detection, but there's no correction. No correction. If there is an error, بنعمل ايه? We drop the packet and we request retransmission. That's all we can do, صح? Yes. But retransmission requires delay and retransmission. طيب. For lower layers, we can provide error correction, not only detection. Not only we detect that there is an error, we detect the location of the error. When we detect the location of the error, we know what to do. If it's 0, toggle it to 1. If it's 1, toggle it to 0. Okay? So, طبعا, by having different combinations of redundant bits, you have some limitation on the number and the locations of the errors that you can correct. So the more bits you have here, okay, the more combinations of errors you can correct.
There is a specific size?
Yeah, we don't have to quantify the size now, but the more redundant bits you have here, the more ability to be able to correct more combinations of errors. Okay? And if the size of these redundant bits is short or is low, this means that you can correct less combination of errors. So that's what this here explains. So from coding scheme 1 to coding scheme 4, the amount of error combinations that you can correct, they get lower and lower. Which means that these redundant bits, in terms of size, they get lower.
So
which means that you can get higher bit rates. Because these redundant bits, they consume some overhead. Okay? So by going this way, you reduce the size of the redundant bits, which means that you can increase the data bits, but it's risky because you don't have any error correction. So for example here, CS4 has no error correction whatsoever. It does not provide any error correction. خالص.
So there is trade-off there.
Yes, بالضبط, exactly. That's exactly what we want to do. That's exactly what we want to say يعني. إن هو there is a trade-off. So by going this way, we reduce the overhead, but this means that we reduce the number of error combinations that we can correct. Okay? So typically, this trade-off can be addressed easily if we can say, okay, so based on the channel state, if the channel state is really good, so we don't have to provide error correction. So we can use a CS4, which means that we can use higher data rates. If the channel state is really low, which means that we have a very bad channel, so the probability of error is high, so we better use CS1, which will give you higher combinations of errors that you can correct. But unfortunately, this adds overhead to the data, so you can get up to 72.4 kilobits per second only. This is part of the resource allocation. So the resource allocation doesn't necessarily have to allocate only time slots. It allocates everything. It allocates the coding scheme, time slots, frequency. All these can be considered resources that I can allocate. And the input, that's what we talked about. And the input to that is a channel state, the queue state of the mobile station, and so on. So based on input information, I run certain logic, intelligence, and then I say, I need to use this coding scheme in this time slot, or I need more time slots, less channels, more channels, and so on.
There's error detection in CS4.
Error detection? Yeah, error detection has to be there. Error detection has to be there.
It's less than CS4.
But there's no error correction. Yeah.
Oh. There is no error.
Error correction. Error correction, no. We don't have error correction in CS4. Yes. But we have a checksum. Checksum is different. It's not part of the coding scheme. Checksum gets sent as part of the header with the data for error detection, not correction. تمام كده؟ So based on this table, you can estimate the data rate that this user can get based on the class of the mobile station. Okay? So based on the class of the mobile station and the coding scheme, you can estimate the maximum uplink data rate and downlink data rate. Okay? Based on how many time slots it can have uplink and downlink, and what coding scheme is assigned to this mobile station. So you can say maximum data rate for uplink is that, and maximum data rate for downlink is this. But the total, I can allocate uplink and downlink. Okay? So this is the last thing. So as we can see, this is the interaction between the main architecture of GSM and the GPRS architecture. As we can see here, in addition to the MSC, now we have a serving GPRS support node, and we have gateway GPRS support node. And we have the GPRS register. Those are the three major components. The implication of this is that you have new interfaces defined. You have GI, GN, GB, okay? So all these interfaces are packet switched interfaces, okay? So again, as we said, GPRS register is used to store the addresses, the IP addresses of the mobile station. And this serving GPRS support node is used to perform the functionality of the MSC for packet switched and the and for authentication and billing and all of this. By the way, billing here is based on what? For circuit switching, billing is based on the time of the voice call. Okay? Billing here is based on what? On the data, on the amount of data, not necessarily the time. And this is the fundamental difference between circuit switching and packet switching. Because for circuit switch, I establish this circuit for you, whether you use it or not. It's consumed already. So this way, I will charge you for the time that you use these resources. Now, the billing for SGSN is not based on time anymore. It's based on estimating or calculating the number of downloaded packets in the uplink and the downlink. Okay? So you get charged by the amount of bytes, not by the time. That's why the entire billing process is different. Okay? For high-speed circuit switch data, even though it provides higher data rates, but it's still, the billing is still based on the time. And that's also another disadvantage or limitation in high-speed circuit switch data. Because I have to do that. I have to do that. Because all these resources are dedicated. So GPRS is the first standard that starts to charge by the amount of bytes, not by the time. So the reflection of this on the layered stack. So we talked about some of these layers in the stack for DSM. There are some differences for SGSN and for GGSN. We see that these interfaces are introduced to the architecture or to the layered stack, which means that all these layers have to be specified from scratch. So for example, from BSS to SGSN, we use frame relay, which was not part of the architecture. Tamam? We use something called BSS GPRS protocol, which is totally different. So obviously, this is in the routing layer, and this one is used for providing quality of service. This one is used to provide quality of service, to introduce the traffic classes and all of this. We have here what we call GPRS tunneling protocol, which is a new protocol that GPRS defined, which uses either UDP or TCP, okay, to communicate with the GGSN and with the external networks, based on whether there is a probability, or there is a reliability requirement or not. If there is a reliability requirement, we use TCP. If there is no reliability requirement, we use UDP. Okay, so that's why here we can use UDP or TCP. We have something called subnetwork data conversions protocol. This is a protocol that works on top of the network layer, or actually it's in the transport level, to provide different levels of reliability depending on the base station subsystem, depending on the cell quality itself, depending on the channel state of the users within the cell. So you can provide different levels of flow control and error control and stuff like that based on the current measurements, in one cell. So based on the fact that the channel state of this user is like this, so you can increase or decrease the level of reliability and the flow control and so on. So it provides sort of consistent or convergent behavior based on the dynamics of the cell, based on the dynamic behavior of the mobile station. Okay? Yani again, luckily you don't have to memorize the layered stack, but there are some high level.
I wanted to ask, you need to know exactly
ما أنا بقول ما أنا بجاوب السؤال. You don't have to memorize the layered stack, but you need to sort of يعني know the high level objectives of GPRS. So you need to know that GPRS is required to provide quality of service, and what are the means or the techniques used to provide this quality of service, reliability and delay, coding scheme, things like that. These are required. Okay? Yeah, I think that's it.
Can we have a review session for the midterm?
Yes, please.
Like to know exactly, not to know exactly, but to know